Hello and welcome to Chemistry the Right Way with me, Mr. Wright. And on today's 15-minute tutorial, I'm going to be talking about fundamental particles, nuclides, and hopefully we'll get to isotopes. All these things are really interconnected, and all they're to do with is the structure of the atom, the actual fundamental bits that make up the atom. So first off, we have three fundamental particles. They're called fundamental particles historically, actually, more than anything else. We actually now know, modern science has gotten to the point where we now know that even the fundamental particles are actually made up of more fundamental particles, and even they are now being investigated to find out whether or not they're made of even more fundamental particles, to find out what is the truly smallest, tiniest little building block of the universe. But for chemistry, the most important part is that we have an atom, and an atom is where chemical properties begin. Once we get subatomic, we're talking about just physics. So, our fundamental particles, three fundamental particles, are, in order of discovery, electrons. We give them the symbol E neg, lowercase e with a negative. That's their, what we call, absolute charge. The negative is actually just a -1, but the actual amount of charge on an electron is like 10 to the -19th, but it's the same, it's the exact mirror, it's the same as on a proton, P plus, in order of discovery, right? Electrons, protons, because one has a negative 10 to the -19th, the other one has a positive 10 to the -19th. I know charge is measured in units called coulombs. But we don't need to worry about that bit. We've got electrons, and they are on the exterior part of the atom. It's actually, fundamentally, they can't exist inside the central part of the atom called the nucleus. In classical physics, it gets a little bit more complicated when we talk about quantum mechanics. But okay, so we have electrons, protons. Okay, that's the big positive that was found via the gold foil and beyond experiments, and then eventually N0. That's the neutral neutron, and that's what neutron actually means. So we've got electrons, protons, and neutrons. Now together the protons and the neutrons make up something called nucleons. That's just because they live in the nucleus, okay? Electrons don't, protons and neutrons do, and if you remember, it's these two that make up the great mass, okay, that can really give atoms their actual mass. So everything around you, even you yourself, however much if you stand on the bathroom scale, however much you weigh, it's really just the mass of all your protons and neutrons more than anything else, okay? Now, when we build up atoms from these building blocks, let's start off with the simplest one of all. We can start off with hydrogen. And when we talk about atoms, we're going to need at least one nucleon and one non-nucleon, or one electron. And the thing that we're going to need is we need something neutral. So if you take a look at this, our only way of building an atom is we have to have an equal number of electrons and protons, and that's exactly what hydrogen is. Hydrogen is just simply a tiny little proton, right? That really, really small, really dense bit, right? A lot of mass in a really small volume. Incredibly dense, and then around it, spinning around, again classically in classical mechanics, we have that electron. So we've got a positive center and a negative exterior. That's hydrogen. Now, an atom of hydrogen, you've got to remember, has never ever known that it's been called hydrogen. Even though it's the most ubiquitous stuff in the entire universe, it's actually, it doesn't know the name that we call it. And, if you're in China, or if you're in Bantu tribes in Africa, you might have a different name for that same element. So the names are just something we put on them, right? But anyway, here we go. We give it the symbol H. And this is where our nuclides come in. So that symbol H, we can now add to that a little bit more of an explanation of what's going on. And this is what we call nuclide notation. And a nuclide is just a very specific description of an atom. So what we do is at the top upper spot here, we're effectively telling the total number of nucleons. So that's going to be the nucleon number, okay? So for our hydrogen, it's got one proton, one electron, only one proton, right? So one proton right here. That's our nucleon number, okay? And then underneath we put this very important term, which is the atomic number. Now this is really important in chemistry because the atomic number is a reflection of how many protons you have in that nucleus. Because the number of protons in the nucleus dictates the number of electrons that orbit the nucleus. And the number of electrons gives rise to the arrangement of electrons, which then gives rise to the chemical properties that that particular atom is going to have. There's all a little bit of nuance in this in terms of like how far we push chemistry, but that's effectively the fundamental like bit of it. This is going to be our atomic number. I don't make up the rules. The number of protons, the atomic number Z, and then the number of nucleons, capital N. So N up here is 1 for our hydrogen. How many protons does it have? Atomic number 1. So our nuclide notation for standard 1 hydrogen, or the nucleon 1 hydrogen, nucleon 1 hydrogen is 1 over 1H. And we can go along and we can take a look at all other different kinds of atoms, right? And so, for instance, what is fundamental to life here on planet Earth, and probably in the entire universe, is 12 over 6C. Now, an important point here is there are 12 things in the nucleus. 6 of them are protons. How many neutrons? It's the difference between them. So it's got 6p plus, 6 and zeros. So how many electrons does it have? Well, because there's nothing written in this upper right portion of the symbol, it's neutral. So there's a balance. So that means that there's going to be 6 electrons. Protons plus electrons, right? Positive plus negative equals 0 for right there. The important point also is that because the nucleons give us our mass, this number here is going to be a very, very close approximation of the mass of the particular element. The mass of carbon, if you take a look on a good periodic table, is going to be 12.0107 atomic mass units, or Daltons is the actual symbol that we use for my UPAC. And it's not a whole number, right? It's not a whole number. We'll get to that when we talk more about isotopes. But if we round, that gives us a basic idea of probably the most common of the types of carbon. So let's take a look at something else, something close to my heart. I once got a text after doing a big long race, and it's like, how are you feeling afterwards? And I texted back to a friend who happened to be a chemist. I texted back, tough race, but still 56/26. So I texted back 56/26. Well, if we take a look at that, what that means is 56 over 26. We take a look on a periodic table. What is element number 26, right? Start off with, a periodic table. You got hydrogen, helium, lithium, beryllium, and you keep on going down and down and down and down and down. And the 26th element by atomic number Z has that symbol, and that means iron. So this is called nuclide notation. If we take a look at our iron right here, we've got, let's take a look, 56 things in the nucleus. That gives iron an approximate mass of 56.253. I don't know what it is off the top of my head. 26 of those things are going to be protons, which means the difference between the two, it must have 30 neutrons in its nucleus. Now, an important part about that is, as we go further and further down the periodic table, right, the number of neutrons is going to become ever more higher than the number of protons. Or in other words, as the number of protons goes up, the number of neutrons starts to rise at a curve. Okay? So by the time we get down to uranium, right, uranium, practically speaking, the last, heaviest, most massive, naturally occurring atom here on planet Earth, we end up with a nuclide with this description, where we've got 238 over 92U. Okay? So that means there are 92 protons in the nucleus. And how many neutrons? Well, it's 238 minus 32. So it's going to be 146. Yeah? That's a lot of neutrons, right? 92 to 146, almost a 1 to 1.5 ratio. So, these are our nuclides. Now let's just take a little bit, take a look at an atom that has distinct nuclides and what isotopes are. Okay, so isotope. Isotope, we can break that down into two pieces in terms of chemistry. Iso and tope. Iso always means the same. It's the same. Right? We have, in chemistry, we have things like isobars. That means same pressure. Isotherms, same temperature. Same. And then topes is literally type. Okay? Isotopes. So, there are two naturally occurring nuclides of hydrogen. Let's go back and take a look. Okay? And those isotopes are as follows. There's very, very commonly 1 over 1 H. Then there's 2 over 1 H. Now if you take a look, the symbol remains the same, but the nucleus is different. Let's take a look. Here we've got one thing in the nucleus, and it's got one proton. That's it. That's its nucleus. There are about two things in the nucleus, and one of them is a proton. So I've got a neutron here. The difference between these two is one little neutron. But that means that the weight of this stuff is practically twice the weight of this stuff. Okay? There is also, so this is a nuclide. This is one hydrogen. This is 2 hydrogen. There's another nuclide that is unstable and has to be manufactured in nuclear chemical processes, and that's 3 over 1 H. 3 over 1 H is 3 things in the nucleus. One of them is a proton, so we've got 2 neutrons, okay? So we've got no neutrons, 1 neutron, 2 neutrons. Okay? These together, because they have the same number of protons, they've all got the same number of electrons. They've all got 1 e neg. All of them. Because of that, their chemistry is ridiculously similar. It's very, very difficult to separate any of these out by chemical purposes, by chemical methods from each other. Very, very difficult. I mean, practically speaking, impossible. So, we call them isotopes because they're the same type, they're the same hydrogen, even though they're individual nuclides. Does that make sense? Should do, right? Last piece. We call this a nuclide, this is a nuclide. This 3 over 1 H, right, has got very bizarre properties because it's unstable, and so it's radioactive. And so because of its radioactivity, we actually call it a radionuclide. Radionuclide just means a nuclide that is an isotope of an element, and it happens to be radioactive. More on radiation later on. Last piece is, we call this hydrogen, hydrogen, hydrogen. This has another nickname. Deuterium. Deut meaning 2, and then here we have tritium, tri meaning 3. And some of you may actually have a little bit more experience with tritium than you think. They used to paint glow-in-the-dark things for certainly military purposes out of paint that has tritium as its basis, its basic solvent. Because tritium is that stuff that glows, that eerie sort of green glow that lots of radioactive stuff doesn't, but tritium happens to, and that's what makes it kind of unique and special. Alright, thanks very much. See you next time. Don't forget to click like, subscribe, and we'll see you next time. Bye.